Hey guys, today in this video we will discuss about the Mayer's relation. Now, the Mayer's relation is quite familiar to students of thermodynamics, but it is really interesting to derive it. Let's take a look. Before we even begin, we must take a look at some of the thermodynamic terms. And at first we have the temperature. The temperature, the standard definition goes this way. It is nothing but how hot or cold something is. Then we have the change in temperature, delta T. And the change in temperature is nothing but the difference in temperature of two bodies. Then we have the internal energy denoted by U, and the internal energy is the whole energy of the system. Then we have heat. In thermodynamic definitions, the heat is the energy in transfer to or from a system by mechanisms other than thermodynamic work or transfer of matter. We denote heat by H. Then we have a really important term. It's called the specific heat capacity. The specific heat capacity denoted by S, or let's rather have C instead of S. So the specific heat capacity is the amount of heat that is required to raise the temperature of a unit mass of a substance by 1 degree Celsius. Now, we all know that a thermodynamic process can occur either at a constant volume or at a constant pressure. Now, let us see what happens in a constant volume process. In a constant volume process, so I have a cuboid. It has a volume, let's assume V, and I have m mass of a gas inside, m mass of gas. Now what I'm doing, I'm heating this up. I'm supplying heat. Let's assume that no amount of heat can flow out of the system. No heat flow outside. So I can only heat the system up and no heat can flow out of the system. So as I heat up the system, what happens to the internal energy? The internal energy of the system increases as I supply more and more heat, and this increases the temperature. We all know that the internal energy of a system is directly proportional to the temperature. Now, what is the volume of the system? The volume of the system is nothing but the volume of this cuboid, and this volume always remains the same because the cuboid always sustains its shape. So the volume always remains a constant. Hence, as we supply heat, the internal energy increases and the temperature increases. So let's assume that at first the temperature was T1, and as I supplied heat, the internal energy increased and the temperature now becomes T2. The change in temperature delta T is nothing but the temperature difference. It is T2 minus T1. Now, how did this temperature change occur? Because I have supplied heat. And how much heat I have supplied? This is nothing but the specific heat capacity times the temperature difference. So the heat supplied, H, is equal to C into delta T. And we know that specific heat capacity is the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius. Since we have m mass of the gas, the total heat supplied is C into delta T into m. And what is this supplied? Where did it go? This heat supplied increased the internal energy of the system. So the change in internal energy is nothing but the heat supplied. So we have delta U is equal to C into delta T into M. And now instead of C, let us use CV. Why we use CV? We'll talk about it later. But please be informed that CV is different from CP, which is the heat capacity of a system, with the specific heat capacity of a system maintained at a constant pressure. Let us take a look at the constant pressure process. Constant pressure process. Here we have a system to which a piston is attached, and we have the same m mass of the gas, and we are heating this up, and as we heat the system up, the internal energy increases. But the pressure of the gas also increase. And what happens then, since the pressure has to be maintained in the constant pressure process, the piston rises up. So as I supply heat, the piston rises up by a small amount. And why the piston rises up? Because the pressure inside has to be maintained. And when this piston rises up, the volume changed by delta V. So the work that is done to raise the piston up is nothing but W is equal to P into delta V. This is the simple derivation and I know you can do it easily. So let's move on. And the as I supply heat, the internal energy of the system increases, but the gas does work to move the piston up. Where does this work come from? It comes from the expense of the internal energy. So the internal energy is nothing but the specific capacity times the temperature difference times the mass of the gas minus the work done. Because as I supply heat, the internal energy increases and a part of it is used to move the piston up. So the net change in internal energy is this minus this. This is nothing but the work done, that is to move the piston up. Now let's we all know the ideal gas relation. What is it? We have P into delta V is equal to R into delta T. Now let's assume that the change in internal energy in both the process are the same. That is delta U1 is equal to delta U2. This is the change in internal energy in the constant volume process and this is the change in internal energy in the constant pressure process. Since the internal energies are the same, the temperature difference should also be the same. So we have C into V into delta T into M is equal to C P delta Tm minus P delta V. Here in the constant pressure process, the specific heat capacity is denoted by Cp. Okay, so no confusions there. This will be different from Cp. That is what I am going to explain now. And let's assume that m equal 1, that is we have used a unit mass of the system. Then this relation becomes C V into delta T is equal to C P into delta T minus P delta V. And what is P delta V? From the ideal gas relation, P delta V is nothing but R times delta T. So we have C V into delta T is equal to C P into delta T minus R delta T. Now Cp minus Cv into delta T is equal to R into delta T. And then what is Cp minus Cv? It's nothing but R. R here is the universal gas constant. He is a really interesting guy and we will talk about him in a future video. And now take a look at this. Since R is a positive value, we have Cp, which is the specific heat capacity at constant pressure, is greater than the specific heat capacity at constant volume. Why is this? Because more amount of heat has to be supplied in a constant pressure process to get the same temperature difference as in a constant volume process. And why is this? Because in a constant pressure process, the gas does work on the system to move the piston up, and this work comes from the expense of its internal energy. So we have to supply more heat in a constant volume process, in a constant pressure process, we have to supply more heat in a constant pressure process so as to observe the same temperature difference as in a constant volume process. So, and this relation is called the Mayer's relation, and it was obtained, this relation was first obtained by Julius Robert Mayer. He was a German physicist and one of the many founders of thermodynamics. And Hope you understood what Mayer's relation really mean, and hope you like this. Do like and subscribe my channel. Thank you all.